Hello everyone, I'm Huang and I'm here to present our work, Video-Based Motion Retargeting Framework Between Characters with Various Skeleton Structure. This is a joint work together with Takashi Kanai. Fans of anime and manga often create character animations where they animate their favorite characters dancing just for personal interests. When they make these character animations, they animate 3D character models using motion data. Usually, this motion data is made with technologies like motion capture and motion tracing, but these methods have drawbacks, such as requiring high-cost equipment or being highly labor-intensive. On the other hand, thousands of videos get posted every day on sites like YouTube. Our research is all about making it easier to people to create their own character animations. We can look into extracting motion data from monocular videos to bring all sorts of characters to life. So back in 2020, a deep learning framework for motion retargeting between characters with varying joint counts was proposed. It employs an encoder and a decoder to achieve retargeting among characters sharing similar topologies using pooling methods. However, it's important to note that this network primarily targets 3D motion capture data. Our goal diverges slightly. We aim to adopt motion extracted from videos through deep learning to different characters. In essence, we are using motion data extracted from monocular videos as the source motion for our retargeting process. So we propose a framework composed of two networks to handle data extracted from videos. This involves extracting motion data from videos using two-stage pose estimation and then feeding it into the skeleton-aware network to generate retargeting results. However, our experiments identified three problems. First, the extracted motion data often contains noise and its data structure may not be compatible with the retargeting network, leading to a failure in reconstructing the extracted motion data. And the second issue is that video data is not used in the training process, so resulting in the loss of some information in the result motion. Last, in skeleton-aware motion retargeting network, when characters rotate more than 180 degrees, the result movements become unnatural. So to address these three problems, we have proposed specific solutions. First, we propose a pre-processing method that processes data after extracting 2D poses from videos to create stable 3D motion datasets adaptable to skeleton-aware motion retargeting network. Next, by using the information from the 2D poses and adding new loss functions, we generate a result motion that more closely matches the original videos. And we propose a method using a loss function for the root node rotation angle to solve the rotation problem. As for the overall process, we train the retargeting network using our created motion dataset, and during testing, we use the pre-trained model. I will go into more detail about these three components next. First, let's start with the pre-processing to turn the motion data we extracted from videos into suitable training dataset. Our framework employs a pose estimator, which uses open pose to estimate 2D poses from the video and then convert this into 3D poses. In case where open pose estimation confidence is low for curtained frames, we employ linear interpolation to produce more natural movements, or we just remove those frames altogether if necessary. Also, in skeleton-aware motion retargeting network, a mismatch in things like the rest poses of the source and target characters can lead to unnatural movements in the output. So after we convert the 2D poses to 3D, we do some adjustments like changing the rest poses and the skeleton sizes to ensure more natural and accurate animation results. Now about the second issue, where the videos are not really used in the retargeting network, we add loss functions of the skeleton-aware network. The original loss function in the network don't refer to the original video data, leading to the animated character's feet lower than the original video. So what we are doing here is adding a 2D root and end effector velocity loss function. Also to address issues like the character's balance being off or the head direction looking unnatural, we are introducing a balance loss function. This function calculates the difference in the direction vectors of the head node between the source and the target characters. And moving on to the third problem, when the root node of a character rotates more than 180 degrees in the retargeting network, the movements ends up looking unnatural. This could be because the retargeting learning doesn't have enough rotation information, so we add a loss function that focuses on the rotation angle of the character's root node. We also tried using 60 rotation representation instead of quaternion in the training process, but we find that adding a loss function is a more effective way. As for qualitative evaluations, we successfully transferred motion data from a video to mixamo character and models. The video we used was a simple single-person monocular video, like the ones you could find on video sharing platforms. And in our results, the animations created using our method can accurately mimic the movements seen in the videos, regardless of the character. These videos are made by ourselves using smartphone. As you can see, we can make character animations through these videos. It can even handle retargeting of random movements, such as those found in the down sequences. To demonstrate the effectiveness of our method, let's look at the steps involved. First, pre-processing the data before using it for training our retargeting network made the character's movements become more natural. Furthermore, when we compared the results before and after adding a 2D velocity loss, we observed that the character's leg movements closely matched the video. Last, after adding the balance loss, the overall movement of the character, especially the angle of the hips, appeared much more natural. Let's dive into the impact of our solution to the rotation problems. The results clearly demonstrate that our root rotation loss effectively generated the correct rotation, and the 60 rotation representation can also solve the rotation problem, but the movements of the character is unnatural. So to do a summary of our research, we implemented a pipeline for generating character animation from monocular videos. We proposed a pre-processing method that generates stable training motion data sets, introduced two loss functions to make more video-like animations, and use root rotation loss to solve rotation problem in skeleton-aware motion retargeting network, and we validate the effectiveness of our proposed method through qualitative and quantitative evaluations. As for the quantitative evaluations, we have proposed two quantitative metrics, relative distance metric and the relative velocity metric. Our method demonstrated better results in both of these metrics. You can read our paper for more details. And for future directions, we want to add depth information in our pipeline, take the context into consideration in resulting character animations, and achieve motion retargeting between characters with different numbers of end effectors. That's all. Thank you.